On January 19, 2006, humanity strapped a grand piano-sized box to the most powerful rocket available and broke a record that still stands today. New Horizons became the fastest object ever launched from Earth, tearing out of the atmosphere at 36,000 miles per hour. It has now traveled over 5 billion miles into the dark. But here is the paradox: to send high-definition images of cryovolcanoes and nitrogen glaciers back from the edge of the solar system, this spacecraft relies on a transmitter with less power than a refrigerator light bulb. Despite this extreme limitation, we are still receiving data from the twilight zone of our star. How is it physically possible to track a 12-watt signal across 50 astronomical units? And looking at the failing nuclear battery, exactly how much longer will we be able to hear it scream? To understand the reality of this mission, you have to understand a counterintuitive detail about its timing. When New Horizons was designed and built, it was destined for the 9th planet. But just months after it launched, the IAU voted. The spacecraft left Earth aimed at a planet, spent 9 years sleeping in the dark, and woke up arriving at a dwarf planet. The original mission was a reconnaissance of the Pluto-Charon system, a region no machine had ever visited. But the physics required a special circumstance to even make this possible. We couldn't carry enough fuel to slow down, nor enough to get there fast enough on engine power alone. The success relied on a rare alignment, a gravity assist from Jupiter. New Horizons stole momentum from the king of planets, increasing its speed by 9,000 miles per hour and shaving 3 full years off the trip. This distinct orbital ballet allowed for 3 key achievements that rewrote the textbooks. First, the heart, or Sputnik Planitia. We expected a dead, cratered rock, but we found a churning sea of nitrogen ice, circulating like a lava lamp and erasing craters. It is geologically alive. Second, cryovolcanoes, specifically Wright Mons, a mountain 90 miles across that spews ice slush instead of lava. And third, the blue halo, a thin, unexpected haze layer in Pluto's atmosphere that glows blue at sunset, proving complex weather patterns exist at the edge of the void. It is easy to confuse New Horizons with its predecessors, the Voyagers, but their paths represent 2 divergent philosophies of exploration. Voyager was the Grand Tour. It swept past the gas giants, utilizing gravity assists to swing up and out of the planetary plane. New Horizons was a sniper shot intended for the 3rd zone, the Kuiper Belt. While Voyager is currently in interstellar space, New Horizons is technically still within the solar system's debris field. Here is the current status comparison, which feels counterintuitive. New Horizons had a faster launch speed than Voyager. However, Voyager 1 is currently moving faster and is much farther away. Why? Because Voyager received multiple massive gravity kicks from Jupiter and Saturn in the 70s. Think of it this way: relative to human capability, New Horizons is a sprinter who exploded out of the starting blocks. Voyager is a marathon runner who started 30 years earlier and caught a ride on a bus for the middle 10 miles. New Horizons will never catch up to Voyager. It will remain the lonely explorer of the middle ground. To understand where the probe is now, we have to define the boundary it crossed. People often conflate the Kuiper Belt and the Oort cloud, but the difference is the difference between a city limit and the border of a country. Think of the Kuiper Belt, where New Horizons operates, as a flat, icy donut. It aligns with the planets. It's the crumb trail left over from the solar system's formation. It is massive, but it is finite. The Oort cloud is different. It is a massive spherical shell, a bubble that surrounds the entire system, extending halfway to the next star. We can see the transition in the data. New Horizons crossed the orbit of Neptune, the cliff's edge of the planetary zone, in 2014. It took 9.5 years to reach Pluto. It then took another 3.5 years of silent darkness to reach its next target, the contact binary Arrokoth. We are currently moving through the density of the donut, scanning for dust and debris that tells us how our Earth formed 4.5 billion years ago. So, here is the core mystery, the miracle mechanism. How do you stream high-resolution photos from 5 billion miles away using a radio transmitter that draws 12 watts of power? For context, your refrigerator light is likely 15 to 40 watts. We are talking about a signal so faint it whispers against the background radiation of the universe. To understand the delay, we need a perspective ladder. Light takes 1.3 seconds to reach the moon. Light takes 8 minutes to reach the sun. The radio signal from New Horizons takes over 7 hours to reach Earth, traveling at the speed of light. The problem is the inverse square law. As the signal travels, it spreads out. By the time it hits Earth, it is billionths of a billionth of a watt. To catch this whisper, the receiver must be massive. We rely on the NASA Deep Space Network, DSN, specifically the 70-meter dishes in Goldstone, Madrid, and Canberra. These massive ears must be pointed with pinpoint accuracy. It requires a global network because as the Earth rotates, one dish loses the signal and hands it off to the next. If the DSN goes offline, New Horizons is talking to itself. But the receiver on Earth isn't the problem. The problem is the ticking clock on board. Solar panels are useless out here. The sun is just a slightly brighter star in the sky. New Horizons runs on an RTG, a radioisotope thermoelectric generator. It carries a slug of plutonium-238. As the plutonium decays, it generates heat, which is converted into electricity. This is not a renewable resource. It is a dying ember. At launch, the RTG provided 245 watts. Every year, that capacity drops by about 3.5 watts. We are now hovering near the critical limit. The spacecraft requires about 200 watts to function fully. We have already entered the era of power sharing. We can no longer run the heater, the antenna, and the instruments simultaneously. We have to cycle them. We are approaching the moment where we will take the final photo, and then the camera must be turned off permanently to keep the transmitter alive. This mission has not been a smooth ride. We have faced near-death experiences. 10 days before the historic Pluto flyby, after 9 years of flight, contact was lost. Silence. The control room went cold. The main computer had been overloaded by a command sequence conflict and rebooted. The solution? The automated autonomy software recognized the failure, switched to the backup, B-side, computer, and pinged Earth in safe mode. Engineers had 72 hours to diagnose and upload a fix, or the entire Pluto flyby would have been recorded as blank static. Then there is the issue of stability. To survive the long cruise between targets, we can't use thrusters to hold the camera steady constantly, that wastes fuel. The solution is spin stabilization. The probe spins like a top during cruise phases, keeping it stable without burning propellant. We only depend for encounters. But the next challenge is thermal. As the plutonium cools, the waste heat that keeps the fuel lines from freezing is diminishing. If the hydrazine fuel lines freeze, the thrusters fail. If the thrusters fail, we cannot point the antenna at Earth. Game over. Engineers are currently rewriting code to use the heat from the electronics themselves to keep the fuel lines warm. We are now in the final act. Current projections suggest we have enough power to operate the transmitters until the mid to late 2040s. That gives us, at most, 15 to 20 years remaining. However, the scientific utility may end sooner. By 2035, the power may be too low to run the heaters required for the instruments. We are counting down the days. This is a finite connection. There will be a specific Tuesday, or a Thursday, roughly 2 decades from now, when the DSN listens for the carrier wave, and hears only the static of the cosmos. Launched in 2006, running on processors slower than the first PlayStation, New Horizons has achieved the impossible. It turned a point of light into a world of heart-shaped glaciers and volcanic ice. It is a piece of ancient human technology hurling itself out of the solar system. Even after the battery dies, and the transmitter falls silent, the craft itself will continue. It will drift through the Oort cloud and into the galaxy, a silent monument to the time we dared to look at the horizon and sail past it.